In this second part of the .numerics plugin functions, we're going to talk about functions that are used for the numerical solution of ordinary differential equations. In a separate playlist, I'm going to talk about numerical methods. So this can be a preview here by applying this particular function. So let's start by looking at the problem of solution of linear ODEs. I'm going to write out for you the specifics of the generic problem of solving a linear ODE solution. What we're going to be solving here is what is called an initial value problem of the first order. And so that can be represented as a first order derivative dy and dx equal to a function d of xy that will be solved numerically in the interval from x1 to x2. Of course, x1 has got to be less than x2. And that range is divided into n intervals. And so the parameter that we're going to use in this solution is called ANTBLS. That will be the n intervals. And so that the initial value for the initial position x1 is equal to init. Okay. So suppose that my differential equation is given by dy x by sine of x plus cosine of x. So the initial value is equal to 1 when x1 is equal to 0, and the interval solution ends up at x2 equals 5, and we have divided that into 10 intervals. The .numerics function offer two functions actually for solving what is called non-stiff ordinary differential equations, and those will be the Adams-Moulton and the explicit Runge-Kutta of order 4-5. Again, if you want to know about the details, look them up online, Adams-Moulton and explicit Runge-Kutta of order 4-5. I'm just doing the solution right here. And so you call the function dn Adams-Moulton with the initial value, x1, x2, number of intervals, and the function that describes the right-hand side of this ordinary differential equation. And we did Adams-Moulton and explicit, and we get basically exactly the same. We solve some discrepancy right in the last value, but in the fourth decimal. Now there's something called the stiff ordinary differential equation, and that's when in the right-hand side equation, in the right-hand side expression, you have a term that varies faster than the other. For example, in this case, this multiplication by 1,000 makes this value to change much faster than cosine of y. And so in that case, .numerics offers two functions. I'm going to go to .numerics here, and these are the Gears BDF. It's called the Gears BDF method, and the implicit Runge-Kutta of order 5 for stiff equations. And so the call to the functions are like these: dn underside Gears BDF, or dn underside explicit RK45 with the same type of parameter, initial value x1, x2 intervals, and the right-hand side of the equation d. And so I calculate the two values here, and they come out about the same. Now, if I go from 0 to 5, we can see that the value goes quickly from 1 to 123. So there's like a lot of variation between 0 and 0.5. If I want to see what's happening there, I could repeat my calculations by changing the initial values from 0 to 1 and show me more detail. And that's the interesting thing about stiff ordinary differential equations, that they could change very fast in a short interval, and then they go changing relatively slowly in the subsequent intervals. And so this is the idea. I just want to show you the methods that are available. And if you want to look up the methods, go onto online and find the names referred to, which are presented in the listing of the functions for .numerics. And those will be Adams-Moulton, explicit Runge-Kutta of order 4-5, Gears BDF, implicit Runge-Kutta, and for linear algebra, you got eigenvalues, eigenvectors, and the other methods that were presented in the previous video. This way, we end this particular video.